So, what on earth does a steaming cup of coffee have in common with the ultimate fate of the entire universe? I know, it sounds like a riddle, right? But the answer connects them perfectly. You see, both of them are governed by the exact same, completely unbreakable laws of physics. So let's dive in and explore these fundamental rules that literally run our world, from our kitchen counter all the way to the cosmos. Our whole journey kicks off with a simple, everyday puzzle. A little mystery you've probably experienced 1,000 times and never really given it a second thought. But, believe it or not, solving this one little thing is going to give us the key to understanding some of the most profound principles in all of science. And here it is. This is the puzzle. I mean, it seems obvious, doesn't it? A thermos is built to keep things hot, and a mug, well, it just isn't. But what is really going on there? Why does that heat seem so desperate to get out of the mug, and how in the world does a thermos manage to stop it? To answer that, we have to get into the heart of thermodynamics. Okay, so to even start to tackle that question, we need a couple of basic tools in our toolkit. And the most fundamental concept, the very first thing we have to nail down, is what scientists call our playground. In thermodynamics, this is called a system. Now, a system might sound all technical and complicated, but trust me, it's actually really, really simple. It's just the thing we're looking at. That's it. It's whatever part of the universe we decide to draw an imaginary box around and study. It's a simple idea, but you'll see it's incredibly powerful. And the cool thing is, this idea is so versatile. A system can be something as simple as a balloon full of gas or a pressure cooker bubbling away on the stove. It can be something as complex as a car engine or even the human body. You can even go huge and define the entire planet Earth as a system. Basically, if you can point to it and study it, you can call it a system. All right, so now that we've got our system, our thing we're looking at, the next step is to figure out how it, interacts with everything else around it. And it turns out there are really only 3 basic ways this can happen, which helps us sort everything into neat little categories. Yeah, this table just lays it all out for us. You've got an open system where both stuff, mass, and energy can go in and out. Then there's a closed system where energy can get across, but mass can't. And finally, you have an isolated system. And that one's on total lockdown. Nothing gets in, nothing gets out. So let's bring this right back to our coffee cup mystery. That mug is a textbook example of an open system. Heat, which is just energy, radiates out into the cooler room. And at the same time, you can see the steam, that's water vapor, or mass, rising up and escaping. Both energy and mass are leaving the system. Now, think about a regular plastic water bottle. You've screwed the cap on really tight, right? So no water can get in or out. The mass is trapped. But if you leave that bottle out in the sun, the water inside is definitely going to get warm. Energy is still getting through. That makes it a closed system. And this, of course, brings us to the thermos. A thermos is our best attempt at creating a truly isolated system. The lid stops the mass from getting out, and that fancy vacuum insulation is designed to stop heat transfer. But notice I said attempt. No thermos is perfect. Your coffee will eventually get cold. A perfectly isolated system is more of a theoretical idea, but a good thermos gets pretty darn close. Okay, so we've set up the game board, right? We know what a system is, and we know the different types. Now, it's time to learn the rules of the game. And these aren't just rules for coffee cups. These are the fundamental laws that run everything in the entire universe. The first law, you've probably heard of this one. It's the famous law of conservation of energy. It just says that you can't create or destroy energy, you can only change its form. The total amount of energy in an isolated system is always, always constant. The way to remember it is simple. You can't win, you can only break even. But then you get the second law, and it's kind of like a dose of reality. It's the one that tells us which way things go. Heat always flows from hot to cold, never the other way around. It introduces this idea of inefficiency and the fact that you can't undo things perfectly. As the famous saying goes, if the first law says you can't win, the second law says you can't even break even. You always lose something to disorder. That little idea of disorder we just mentioned, well, that is everything. It has a name, entropy. And entropy is honestly one of the most mind-bending ideas in all of physics. It's the reason why time only flows in one direction. It's why things break down, why a clean room gets messy, and yeah, why our coffee gets cold. To get your head around entropy, you don't need some crazy equation. All you need is a little thought experiment. So imagine you've got a box with 100 coins inside. You close it up and you shake it like crazy. When you open it back up, what are you most likely to see? Let's compare two possible outcomes. We'll call them states. State A is perfect order. Every single one of those 100 coins has landed on heads. And state B is what you might call disorder, a jumbled mix, maybe 50 heads and 50 tails. So, which one do you think is more likely to happen? Well, let's think about it. For every single coin to land on heads, there is exactly one way for that to happen. Just one. That specific combination out of an ocean of other possibilities. That makes it an incredibly, incredibly unlikely state. And now for the punchline. The number of ways you can get a messy mix, like 50 heads and 50 tails, well, the number it's just mind-boggling. It's so huge, it's hard to even wrap your head around. The point is, there are vastly, overwhelmingly more ways for the coins to be messy and disordered than for them to be perfectly ordered. And here is the absolute key. The universe isn't trying to be messy. It doesn't have a preference for chaos. It's just playing the odds. And because there are just astronomically more ways for things to be disordered than ordered, things will naturally drift towards those more probable, disordered states. That unstoppable trend towards the most likely outcome is entropy. And just like that, we have all the pieces we need. We've defined our systems, we've learned the two fundamental rules of the game, and we've finally gotten a handle on this wild idea of entropy. We are now ready to solve the mystery of the coffee cup once and for all.
So here it is. Here's the answer. The heat in your coffee mug doesn't just want to escape. It's simpler than that. The universe as a whole is just moving towards its most probable state. And a universe where that little pocket of concentrated heat has spread out evenly into the cooler room is a vastly more probable state. It's a higher entropy state. Your coffee gets cold because the laws of probability demand it.
And this simple idea is summed up in one of the most powerful statements in all of physics. It's not just a rule for coffee, it's a rule for the cosmos. In any isolated system, and the universe itself is the biggest isolated system there is, entropy can only ever go up, or at best, stay the same. It's always moving toward that state of maximum probability, of maximum disorder. And that leaves us with one last huge question to chew on. The first law tells us the total amount of energy in the universe is fixed. It's never going to change. But the second law tells us that the universe's disorder, its entropy, is always, always going up. So if you have a fixed amount of useful energy that's constantly spreading out and becoming more and more disorganized, what does that imply for the end of everything? What is the final, most probable state of the entire cosmos?